Huh? We had, there was also checking. I'm not 100% sure. No, we are remote. Yeah. Are we broadcasting? Thomas? Are we broadcasting? Okay. David, if you can hear us, you can take over the screen.
I'm here. Can you hear me?
Yes.
We can, yeah. Go ahead and share your screen. You are sharing. Excellent. Oop, yep.
Yeah, looks good.
Where's the green? Oh, we don't need the green box because we have the thing on the right. Got it. Okay. All right, David, take it away.
Great. Thanks, everyone. So I want to tell you a little bit about how I've been trying to get reliable radial velocities and chemical abundances from JWST near-spec spectra. And before I dive into the details, let me give you a little bit of motivation for what I'm trying to do. So we've known for a long time that in our Milky Way galaxy, there are two stellar disks. There's a thin disk and a thick disk, and the thin disk is generally younger stars, while the thick disk is generally older stars and more puffed up. And we've also known for a while that actually they are chemically different as well. So this is showing the relative alpha abundance on the y-axis versus metallicity. And so the two different populations separate really nicely in chemistry space, with the thick disk stars having higher alpha abundances. So for the last 10 years, we've been trying to figure out like why there is this kind of chemical bimodality, and have now several models that that explain the data, but none of the data actually strongly favor the model. So what do we need to make progress? Well, of course, we need more data. That's always the answer. But we actually need abundance data on other Milky Way mass galaxies. Now, this is essentially impossible from the ground with our current capabilities. You just can't get the signal to noise that you need, and the galaxies are very far away. But we can do this with JWST and NearSpec now to look at stars in the M31 disk. So that's what my team and I did. So we got a successful cycle 1 proposal to use NearSpec to look at one field in the M31 disk, kind of similar to the solar radius. And we also looked at 3 Milky Way star clusters, kind of for calibration and verification purposes, and also got near-cam pre-imaging for targeting and good astrometry. So most of you probably know all these details, but right, we used NearSpec. We use the highest spectral resolution, R of about 2700. That's a reported value, but actually from our experience with the data, due to the undersampling, the resolution is more like 4,000 to 5,000. And we picked a wavelength range of about 1 to 2 microns. Now, the great technological innovation with NearSpec that really allows us to do this kind of science is the MSA, the multi-shutter array. Right, this allows us to open various shutters as needed, and allows us to observe over 100 objects or stars at a time in our field. So this is kind of what we expected to see. These are kind of the some synthetic spectra of our NearSpec data, and just showing that there are lots of features that we can measure, both metallicity and alpha abundances. So we got some near-cam data, and so we were able to, of course, get 2 wavelengths at the same time. Unfortunately, we didn't get all of the dithers we wanted to. There was some kind of failure at the time, but we got enough data to get the photometry and astrometry that we needed. Of course, you guys have seen all these nice images, very fantastic. So the first of the 3 software packages I've been working on is called Prometheus. And this is a new Python-based PSF photometry package that I've been working on the last few years. And we use this to process the NIRCam data. So it's largely based on Peter Stetson's algorithms in DOPHOT. So there's a list of all the things it can do, right? It can do sky subtraction, iterative detection. It has many different PSF analytical models, plus empirical correction tables that can also vary spatially across the image. It can automatically detect or pick out PSF stars and fit the PSF to all of them simultaneously with outlier rejection. And then, of course, it can fit the flux and centroid of all the stars in groups simultaneously, and finally measure and apply aperture correction. So on the right-hand side is a color magnitude diagram of our NIRCam photometry from Prometheus and Red Clump. And so we selected, so one of my undergrads, Charlie Siders, ran Prometheus and also calibrated the photometry using FAT and the astrometry using Gaia DR3. And so we picked the top roughly magnitude and a half of the red giant branch to get our targets. And this is the data that we got back in December of our M31 field. So we have our two near-spec detectors, and at the highest resolution mode, the spectra cross both of the detectors, and we were able to get 6 dithers and 106 stars. And if you zoom in, you can see that the traces overall are curved quite a bit, which is fine. But you also see that the flux is almost all in one single row, and this is because the spectra are very undersampled. So the full width half max is about 0.9 pixels, when for Nyquist you would want at least 2 pixels. So it's both undersampled spatially and spectrally, which has made the analysis and reduction a little bit more challenging. So this is what the pipeline spit out back in October of last year. So if you know what 1D stellar spectra look like, this is not what they should look like. So the pipeline was having problems with extraction last October, and I contacted the help desk, and we tried all kinds of various things. And I also reran the pipeline myself, trying to change all kinds of different parameters, but just cannot get it to work. And I'm sure that since then, the many improvements have been made. But at the time, in order to get my science done, I basically had to write some of my own software to get it extracted properly. So I wrote a new package called Spiderweb. So it does a bunch of things. The main thing that I needed was better extraction routines. So it uses optimal extraction with an empirical non-parametric profile. It also does outlier rejection. It does slit corrections that I'll talk about in a second for rate of velocities. It also can determine rate of velocities and abundances by calling other packages. And so the URL is there if you want to check it out. It's still being actively developed. So just to show you briefly what it does. So here's a 2D image of one spectrum, and you can see that there are a number of bad pixels there. And so one of the first things it does is it creates this empirical 2D PSF. So that's what that looks like here, and deals with problematic pixels, and that uses this PSF to then do the optimal extraction where it weights each pixel by its signal to noise. So this is what the extracted spectrum looks like. So this is what a stellar spectrum should look like. So overall, that works pretty well. One of the issues that we found, though, is there are still some systematic issues with the data. So we see these kind of ripples or wiggles at a few percent level in the spectra. And you can kind of see that here. And we've been trying to figure this out now for over a year, still not really sure what this is from. So the origin is still unknown. It does not look like it's astrophysical. And one way I tried to remove it is just smoothing it in wavelength and averaging over all the spectra we have. And this is kind of what it looks like. But it does not seem completely consistent from star to star. So that's still something we're trying to figure out. And so we had to use to kind of change our normalization routine to try to remove these features. But there's still enough left to figure everything out. So the next thing is to try to get radial velocities of the stars. So I have another package called Doppler that I've been working on for the last several years. And this does a forward modeling of the spectrum. So it uses a machine learning model of stellar spectra. And it then forward models the observed spectrum to the wavelength solution and the resolution. And so this nicely deals with the undersampling in the near spectra. So we have clusters, so 3 star clusters, and so we can check the RV precision. So if we look just at the histogram of our M71 cluster, you can see a very large velocity dispersion of 30 kilometers a second, when in reality it's known to be much smaller than that. And we suspected that there would be slit corrections issues because the star is not completely centered in the shutter. And so when we this shows the star positions in their shutter, and so the pipeline assumes that it's at the center, and so that's going to cause wavelength shifts and RV problems. So if you just plot the rate of velocity versus the expected position of the star in the slit in the dispersion direction, you see a very strong correlation. So that was kind of expected. But then when we remove that, correct that out, we get a RV precision of about 7 to 8 kilometers a second. And we still know that this is dominated by systematics. So if you look at the expected RV uncertainty versus signal to noise, you can see that it should be at a kilometer per second or less. And so this is still dominated by the fact that we don't know the actual position of the star in the slit. We only know the predicted position. So that's still something we're working on to try to improve that. All right, so then we went on to do abundance determination. So here I used 40 grid of synthetic spectra in temperature, surface gravity, metallicity, and alpha abundance, and used this other code called FARE by Carlos Alejandro Pietro to search through the grid. And this also nicely does forward modeling, so that handles the undersampling in the spectra as well. And this just shows 2 examples of the observed and the best fitting synthetic spectrum. So the observed in black and the best fitting in red. And the top one is a Milky Way foreground giant, and the bottom one is an M31 giant that's 7 magnitudes fainter. And you can see that for both of these, we have very good high signal noise spectra, and we have also we can very precisely measure the stellar parameters. We also did a couple verification tests by hand of the abundances. This was done by Vern Smith with the turbospectrum synthetic spectrum code, and we have a number of stars for which we have ground-based apogee data. So these are for the calibration cluster stars, and we found that the abundances match very well with what we get from apogee. I've also recently determined that we can go well beyond just mean alpha abundance. There's information for up to 16 elements in this wavelength range, and with the signal to noise we're getting, we can get precise abundances for all of these elements. And that's still a work in progress, but it's really exciting to see what's possible with these spectra. All right, so what are the results? So on the left, I'm showing the Milky Way abundances in the alpha abundance plane. And on the right is the first preliminary results from M31. And you can see that it looks very different from the Milky Way. The thin disk, low alpha population that we see in the Milky Way is almost entirely missing in M31. And almost all the stars fall along this one kind of sequence, which we call the high alpha sequence, which is the thick disk in the Milky Way, suggesting that the M31 stellar disk is dominated by this thicker high alpha component, which actually kind of makes sense based on the very active accretion history that M31 has had. And just to summarize, I talked about my M31 program with NearSpec. I mentioned three packages. So Prometheus does PSF photometry, Doppler determines rate of velocities, and Spiderweb can be used to do spectral extraction and also run Doppler and the FARA code to determine abundances. And there is a conference proceeding there that describes the main results. And that's it. Thank you.
Say a few words about dithering in the dispersion direction to improve wavelength resolution.
Yeah, great question. So before we got the data, we didn't realize it was going to be undersampled. And so now it's clear that, yeah, you need to do some dithering, some subpixel dithering in the dispersion direction to recover full sampling in your spectra. And this is actually something that we do for the Apogee instrument as part of Sloan. And so the techniques for dealing with the data are there in common. The one technical issue that you need to be aware of is that if you're dithering spectrally, you have to make sure that you aren't moving your star out of the shutter. So it restricts, you have to restrict the stars a little bit. But yeah, that's an important thing to keep in mind for the future.
Got it. One last question. Say a few more words about the promise, the hope, or the challenge of using the actual locations of sources rather than the predicted location of sources to do the correction, the rate of velocity correction.
Yeah, another great question. So part of the issue is that, right, we don't want to, or the general policy is not to take any calibration data or kind of non-dispersed data at a given position. I think there's various concerns there. Part of it is, persistence and latency. So there's not much information in the data itself to figure this out, but there is a little bit. So the one thing that we're trying to do is actually look at the traces. So if there's like a little bit of rotation, then the traces should be slightly shifted and it should vary with position on the detector. So we might be able to figure out a misalignment with a rotation there using the traces. The other thing, so this is Tony Sohn's idea, is that we might be able to use the guiding camera information to at least figure out how the pointing is slightly offset from where we expect it to be. Of course, for that, we'll need to be able to tie the guiding camera to near spec very, very tightly in order to figure that out. But I think there is, promise to making improvements on this for the future.
Perfect. Thank you so much. All right, we're going to move on to Lindsay.
Thank you. Hi, I'm Lindsay Kwok. I'm a graduate student at Rutgers University, and I'm going to tell you about the work that we're doing with observations of supernovae with JWST. And I want to highlight the power of low-resolution spectroscopy for these types of objects. So just to give you a little background on the science cases that we're working towards in supernovae with JWST, we are specifically interested in white dwarf supernovae, and some of the outstanding questions in this field are what are the progenitor systems? Like, we don't know exactly what mass it explodes at, or what the companion star is, whether it's like a red giant or another white dwarf. And then there's a lot of open questions in terms of the explosion mechanism. How exactly does the burning get triggered? And does the burning front propagate like subsonically, supersonically, or some combination? So the tool that we're using to investigate these questions is what we call nebular or late time spectroscopy. At late times, the supernova ejecta has expanded such that you can see all the way through it. You're getting emission lines from the interior, and they're forbidden emission lines because it's very low density. And so that can directly tell us about the composition, the kinematics, the geometry, the ionization, and the density of the ejecta. So this is a powerful tool, and it's made even more powerful with JWST because in the infrared, there are new and more isolated lines. And there's also lines coming from intermediate mass elements like argon, calcium, and sulfur, as opposed to the iron group elements, which is important because they're nucleosynthesized in different ways, so it can discriminate between models. Also, there's just really a small amount of data prior to JWST. Before JWST, we had 7 spectra of white dwarf supernovae and only 3 unique supernovae. So our spectra from JWST looks like this. This is combined with an optical image from a ground-based telescope, SALT. And you can see that these are emission lines. We're directly seeing the composition of the supernova. So in the optical, we're mostly seeing iron. And now in the infrared, we're seeing nickel, cobalt lines. They're a lot more isolated in the mid-infrared. And again, we see those intermediate mass elements. So when we got this down from JWST, our first observations, it was August of 2022. So this is only a couple months after science imaging with JWST started. So we were super excited. This is a comparison of JWST in black compared to Spitzer in blue. And you can see the improvement in signal to noise ratio is just astounding. However, there was a problem initially in the wavelength calibration. You can see that these lines are pretty off. So, for example, this line should correspond with this one, and that one should be over here, and this one should be over here, and so on. So we contacted the JWST help desk, and there was a known wavelength calibration issue. And this is a little bit harder to fix in space than on the ground, because in the ground you can just use an arc lamp where you have lines from, say, neon, and you know what those wavelengths should be at. You observe the lamp, and you calibrate. But here we have to actually use observations from things in space to calibrate it. So at this point, there were very few observations in the LRS. And sorry, I should have specified, this is the low-resolution spectrograph slit mode. So in this slit mode, there were very few observations publicly observable at that time. So we went to the archive, hoping to speed up this calibration process because our data had no proprietary access period. And if you'll look at these gray spectra here, these are spectra taken in the commissioning and calibration cycles of VFTS 822, which is a Herbig BE star, which has hydrogen emission lines. So they're hoping to use these hydrogen emission lines to calibrate the wavelength. I have highlighted in red where those hydrogen emission lines should be. And as you can see, some of those lines are like barely even there. It was a very difficult thing to do. The data quality wasn't fantastic, but we forged ahead. So we bootstrapped this to get centroids and uncertainties on these different hydrogen emission lines and compared that to what we knew the hydrogen emission line wavelengths should be. And that allowed us to see the residual, which is shown in the right. And you can tell there's a really distinct trend. So to correct for this, we tried to fit a function to it. We went back and forth with the MIRI team through the help desk, especially Sarah Kendrew and Greg Sloan were extremely helpful with this. We suggested a quartic fit, but ultimately it kind of overfit the data. And so the JWST team decided to go with a linear times decaying exponential fit. And putting this together, it shifts the spectra over to like the blue and the green. They are two different methods, basically look very similar. And now the wavelength correction is improved even more in the JWST pipeline, but they pushed this to all existing data for LRS slit and all previous subsequent observations. So kind of the before and after comparison after this wavelength correction is shown here. You can see that there's also some flux calibration that happened in the meantime, and it's a really big difference at these short wavelengths. So this is still a work in progress a little bit. Like the data I showed for the Herbig BE star with the hydrogen emission lines is low signal to noise. So some further LRS wavelength corrections that have been done and will be coming in the future. Byler et al. 2023 did an additional correction using a brown dwarf spectrum. They compared it to a model and were able to create an additional correction. So currently that's what we're using on top of the JWST LRS wavelength correction. One thing to note is that we could not do this model comparison to our supernova to begin with, because the supernova has intrinsic velocities that are very high, and so we didn't want to mess up like what the supernova's velocity was versus the actual wavelength calibration. Whereas the brown dwarf, it would be expected to have low velocities, if any. Additionally, some new observations have been taken of a planetary nebula. It was taken with both the LRS slit and the MRS, and so they're actually going to be able to match the wavelength calibration between MRS and LRS. So that's going to really improve things, and that should be coming in the next few months or so, or hopefully sooner. So a few of the things that we additionally after this wavelength correction, some of the analysis techniques that we've been using for supernovae with these LRS spectra is identifying lines. There's not very much data in these wavelength regions, so we are finding new lines. The atomic line list is a great resource if that's something you are working on too. We like to measure line velocities. Velocities are important for supernova ejecta and different models. So using the line profiles, and this is one of the reasons it's important for us to have a good wavelength calibration, is to get those velocity measurements correct. But we can measure centroids and full width half maxima to see how the bulk ejecta is moving and how the different ions, like what locations they are in the ejecta, which the velocity traces. And then we can also derive line fluxes to get ion abundances and masses. And then just to point out over here, even after the wavelength correction, there are these 3 outlying points on my velocity plot. Those 3 are from the shortest wavelengths in MIRI LRS. So it kind of shows that there's some systematic, especially at the lowest wavelengths, where the calibration is still most uncertain. And then I wanted to highlight that there's some other tools that we've been using that I especially like for quick looks and exploratory. I think it's very easy to access, and for someone who might be less familiar with some of the coding techniques, especially say undergrads, if you want to get them involved in a project, I think this is a great place to start. Space Telescope has been developing JDA-Viz, which is like a visualization program. Ori Fox is going to talk about that in the next talk, so I won't say too much. But one thing that we use is SpecViz 2D. And I like to use it specifically for its spectral extraction tool. It allows you to investigate like spectral artifacts, bad pixels, cosmic rays, check your background subtraction, and compare extraction techniques. So just as an example, it's got this nice graphical user interface. You can put where you want your trace to be. You can define a background region. Sometimes I make my background like here it's in the manual mode. I get to choose my width. And then actually what I like about this is you can scroll it through the whole 2D spectrum. So if I zoom in on a region I'm interested in, this is an important calcium spectral feature in our data. And you can see here there's a bad pixel and that's snuck in. during the pipeline calibration in stage 2. So that is in one of the dithered images, but it's not in the one above. So there's 2 dithers, and then when you subtract them, you get like these, and add them back together, you get 5. But essentially, by using this tool to go through and like it immediately gives me a spectral extraction, that's very useful visually. One thing I'd like to see improved, though, is that in SpecViz 2D, it's in pixels versus flux density. It'd be nice if that was wavelength and flux. So, but this helps me recover the actual shape of that line, which is important because that tells us about ejecta geometries. So some other nice tools that SpecViz offers are like basic line IDs and line analysis tools like flux, equivalent width, centroid, and full width half maxima. In the future, some functionality that I would love to see, so if you work on JDAViz, this is for you. It'd be great to have, like I said, flux and wavelength calibrations, possibly like including that within SpecViz 2D. Additionally, I've used CubeViz for the MRS data cubes, and I really like that application. I think it's pretty nice, especially for a quick look. But it'd be awesome to have some sort of tool similar to spectral extraction tool in SpecViz 2D, but with CubeViz with like an annulus for subtracting backgrounds and such. It'd also be nice within CubeViz, if possible, to extract the same physical regions in channels 1, 2, 3, and 4 simultaneously. And then when you do those spectral extractions in these applications, it'd be great if you could return the extracted spectrum with the flux and wavelength calibrations included. And then I just wanted to end with a discussion of MRS versus LRS. Of course, it depends on your science case. For our supernovae, which are point sources, and they have velocities of thousands of kilometers per second, the features are really quite broad. So LRS is a lot less expensive, and that also makes it good for sample building. We're currently at the stage where with JWST this past year, we were able to get 8 spectra of 4 supernovae. So now we're up to a total sample size of 7, including the 3 objects with low resolution data from before. So we're talking really small samples. So as we build this up, I think LRS is a really important tool to use. And then with these high velocities, here's a comparison showing the low resolution data in red. So this is near spec prism and MIRI LRS slit, low resolution compared to the high resolution medium resolution near spec gratings and MIRI MRS. So definitely MRS, like there's advantages. It goes to longer wavelengths and you see some more narrow features, but for something like a supernova that's mostly broad, really the red is capturing most of what you see in the blue. And additionally, the MRS data reduction is a lot more difficult, whereas with the LRS, especially once the wavelength calibration is perfected, it's pretty much good to go out of the box. So thank you for your time, and I'll take questions.
Thank you so much. We did have a question, but it got answered already. It was whether that same scary wavelength error affected the slitless, and Sarah already said that no, there was a different calibrator. So
yeah, thankfully the slitless was all right, but that didn't help us fix the slit. Yeah.
So and then I guess I didn't realize it's a trivia, but we're up to 4 letters now after the supernova things.
Yeah. So supernovae are named by the first supernova of the year is like 2024A, and then it goes all the way through Z, and then you get to AA, and so now AAIQ, AEFX means we're in the thousands of supernovae each year.
It's not 26 to the 4th power options because you just cycle through them.
Yeah, so we haven't gotten to like 2021B something yet. Yeah.
Okay, anyway, thank you. Yeah, that's a lot of data.
Awesome, thank you.
All right, so now let's see. We're going to finish up with posters. Ori's online.
It's online, yes.
Yeah. Would it be better to do Ori last, or doesn't matter at this point? We're already ready. All right, let's just do Ori. So we got 4 posters. Larry, at some point, if you could queue up and get the lapel mic on, that would be awesome. And then the rest of you in sequence, that would be lovely. We got 5 minutes each.
All right, should I go? Can you hear me?
No, yes, we can hear
Oh,
you, but we don't have the screen set up properly here yet.
Okay,
No, we see.
that's fine. I'll just say I do need to go first because I have a date with Neil deGrasse Tyson tonight.
You have to flip your displays. We see your poster in the background. Yeah.
All
There
right.
we go.
Now we can see your poster. Go for it.
All right. So hello, everyone. My name is Ori Fox. I am the recently new Deputy Project Scientist for the Roman Space Telescope here at the Institute. But previously, I was the project scientist along with Cami Pacifici for the JWST Data Analysis Visualization Tool Suite. And that's something I wanted to advertise today. This is an effort that you've heard about and hopefully demoed in the cafeteria this afternoon. This is a tool suite that's been put together by Space Telescope to specifically support JWST data product. This is not necessarily meant to replace all of the great tools that the community has been using over the years, including DS9. However, there was this need for tools as we start to move away from IRAF slowly but surely into the AstroPi era and using great new packages that the Institute is developing along with the community, including SpecViz, SpecUtils, FOTUtils, and packages like that to analyze all sorts of astronomical data. But we wanted to be able to replicate some of the interactive capabilities that you might be used to back in the IRAF days, such as Splot or SpecReduce, where you have an interactive reduction package. And so there's been this push to create an interactive capability, and specifically, we wanted to do that in a GUI format, but not just a standalone tool, but a tool that could be used and integrated within a Jupyter notebook, okay? And the main advantage to that is that you can create these notebooks and you can even use the APIs without necessarily using the widgets. And you can create a reproductive workflow that you're able to share with all of your collaborators. And that is really the primary driver for how this tool started and the look and feel of the tool today, okay? So I really want to stress that because this can be used as a standalone tool, but the real power is integrating it into your Jupyter Notebook workflow. And it doesn't have to be the only tool that you use for your analysis, but it is one of several, okay? And so we have 5 different instances for this tool. And one is the most obvious, InViz. Okay, this allows you to look at 2D astronomical images. Then we have SpecViz, which allows you to look at 1D astronomical spectra, perform some analysis that you might be able to do using the SpecUtils AstroPi package. Okay, so AstroPi is the fundamental package that drives this GUI. Okay, I really want to stress that. SpecViz 2D, which Lindsay just mentioned, you're able to interactively extract your spectra in very difficult situations where you might not feel comfortable setting the parameters within the pipeline. There's also QViz, which allows you to look and analyze 3D data cubes, specifically from MIRI MRS and the NearSpec IFU. And then there's also MOSViz, which allows you to look at multi-object spectra, so a whole series of spectra, ideally coming from an instrument such as NearSpec MOS. However, you could also imagine that you just have a large spectroscopic data set that has some sort of cohesion and a set of similar objects, and you want to be able to compare them in bulk. Okay, and so that's a use case for MOSFETs. So we have a whole set of resources online. We have example Jupyter notebooks that you can clone and run yourself. So I really encourage you to go to our website and check that all out. And of course, we have a lot of online and in-person support this week if you have any questions.
Great timing. Thanks, Ori. Next up, Larry. And Justin, if you could queue up, that would be great.
Good afternoon, everyone. My name is Larry Bradley. I'm the lead developer of the FoUtils package. It's a National Pi affiliated package for photometry and other related tools. I'm here today to talk about recent improvements in the PSF photometry subpackage within FoUtils. The original tools were written by a series of students and a postdoc, and they were a little bit rough around the edges, missing some features, and they were also very, very slow. So I recently rewritten them basically from the ground up to be more performant. They're about 200 times faster or so, and also to add some missing features. As an example, one of the test data sets I was using was a large image with 5,000 sources. It used to take over 3 hours to run in the old tools, and now it takes 40 seconds to run. So much, much faster with all the additional improvements as well. There's a series of tools around PSF photometry. First of all, star finders. Of course, you have to find your sources before you do photometry on them. There's 4 sets of classes there. You can use DAO star finder, RF star finder, etc. This is a NearCam F200 simulated image with IRF star finder. It found all the stars in the image. There's also a gridded PSF model in FoUtils. So this accounts for the spatially varying PSF across the detector. Web PSF can create these grids. It could output them directly in the FoUtils format. You can also read in standard PSF formats produced by J. Anderson or other libraries. You can also make an ePSF. There's tools in FoUtils to build ePSFs from your image directly. This is an example showing a NearCam F200 again, 4x4 grid. Each of those PSFs are 4 times oversampled. And then in the bottom image is showing the ePSF differences from a mean ePSF. The main class for doing photometry, the new one is called PSF photometry. Again, this is a NearCam simulated image on the left. The middle image is showing the fit to that image, only showing the central 25 by 25 pixels. And on the right is subtracting that model. If you look in the centers of those stars, they're all perfectly subtracted. It's just you get to make a bigger model just in the PSF to show the full subtraction. And since it's a simulated image, we know the truth. The truth compared to the actual measured is 0.1% RMS in flux. So very, very good. There's also source grouping tools in case you have crowded fields. You need to fit PSF simultaneously to multiple stars. You can group them using a clustering algorithm. That's available in FoUtils. There's a long list of features there. I'm not going to read them all. The code is developed on Read the Doc. The documentation is available on Read the Docs. The code is developed on GitHub. So if you have feature requests, log reports, you can report them there. And you can also reach out to me on Slack this week. So thank you very much.
Sorry, Larry. Since you left 2 minutes, I'm embarrassed to ask this question, but does the JWST pipeline use this at all, or?
No.
Okay, should it?
Yeah, but not PS. There's no PSF photometry in the catalog.
Gotcha. Okay, and I didn't ask should it yet. We'll have that conversation online. Thank you.
Yep, sure.
Great, thanks. This is good? Yeah, sorry about that. Okay, I'm Justin Perel. I'm an Einstein Fellow here working in the Transient Science group, and I'm going to talk a little bit about more photometry, which everyone's very excited about. This basically came about from very early on similar to what Armin was saying, frantic coding, right when the data was coming out. And I and other people in our group were finding that it was difficult to just get an image and get some photometry for JWST. And there's lots of packages around that are meant to do this, but just for our science, which is supernovae, an isolated source, one source, we don't want to do the entire field, we have a supernova we want to look at, we want to get photometry and multiple filters. That was not really a solved problem for us, all in Python. We just wanted a simple way to do this. So this is where this basically came about. And I would say that the goal of this, for me at least, is not to have a separate package from things like photutils, but instead to bring some of this development along to the point where we can include some of the features that are missing for our specific case of this isolated point source photometry into something like photutils. So I'm just going to show a couple of those specific features. So one is this level 2 example is photometry on level 2 data. PSF photometry on level 2 data is very common, but something that isn't usually implemented because it's so computationally expensive for all the stars in the field is this sort of simultaneous MC-MC fitting with all of the dithered exposures simultaneously. Usually you would want to just do them all individually and then average them all at the end. In a lot of cases that comes out to pretty much the exact same thing, but this is something that's sort of novel and could be implemented for this isolated source photometry. The other thing that we've been playing with and I would say is not really ready for prime time, but we're still developing is this level 3 PSF photometry. So all of the kind of web PSF, which of course we're using here, models are done with level 2, and what we're trying to do is push them to level 3 by basically drizzling level 2 PSF models. And this would enable you to go deeper, as well as it's computationally less expensive since you only have to do your photometry on level 3 images instead of all of the individual dithered exposures. At the moment, this is like a 5 to 10% accuracy type of thing, not 1% or 0.1%, but you get a lot of benefits from it, so we think it's worth kind of continuing this effort going forward. This is all pip installable at the moment, but I will say that there's an ongoing effort here as by Telescope. Basically all the various people that work here that you've seen talk about PSF photometry today are working on a kind of global testing to see when various methods and codes work best for various scenarios. That's ongoing, and I'd look for documentation on that coming in the next, say, month or, well, holidays, so maybe after the holidays, but we'll see. And that will give us a better idea about when things like level 3 PSF photometry versus using something like Dolpho versus something like photutils, when each of these codes will kind of work best. So yep, come and see me if you're interested in some of these kind of niche features. And there should be a poster about this, and there's installation and docs in these QR codes as well. Thanks.
Go ahead, Alessandra, please.
Hi, my name is Alessandro Savino. I'm a postdoc at UC Berkeley. And so with this poster, I just want to summarize some of the work that our team has been doing on the ERS Resolved Population Program the past year or so. And so just for context, this is a Cycle 1 ERS program. Is led by Dan Wise. And the idea is to use web observations of nearby star clusters and dwarf galaxies to develop the tools to work with near-come and nearest imaging of resolved stellar populations, including crowded fields. And so on one hand, our goal is to develop the software packages to perform PSF photometry on near-come and nearest imaging. And so this is basically just a near-come, nearest module for the Dolpho software, which is widely used for crowded field photometry. And so this is available on the Dolpho package. It's just now getting out of beta. We have also new documentation on reader docs that will be coming up very soon. But on the other hand, we can also use these data sets to sort of get a bird's eye view of the current status of web photometric performance for PSF photometry of point sources, and so estimating, many of the little ingredients that go into building a photometric catalog. And so the punchline is that we have looked at a number of different effects of ingredients, and all of them seem to matter only if you care about photometry down to 5% precision or lower, in which case, some of these effects might be relatively important. So just to mention a few here, has been really interesting to see over the course of cycle 1 and cycle 2, for example, the improvement in the flux calibration in NIRCam in this case. And so this is constantly being improved over time as new updates were pushed in the pipeline. We are now basically, this happened first very quickly in short wavelength channels, is more recently in long wavelengths. And so now we are at the point where the flux calibration on a chip-by-chip basis is self-consistent within something like a couple of % levels. Other things we looked at is the status of the web PSF models, and so having this data set allowed us to validate how this PSF perform compared to real data. And the punchline is they seem to do pretty well, except they are still a little bit on the narrow side compared to real observations, and we think this is due to a number of detector effects which are not still properly taken into account. And again, this is an effect which is of the order of 2 or 3% for NIRCam, depends on the filter. It's a bit more relevant for NIRIS, and this is probably due to the different plate scale of the detector. We're still looking into why this happens at the bright end. It might be a mix of saturation and other effects, but we think that especially on the low signal to noise side, this is probably due to the photometric extraction strategy that ECC employs, which is aperture correction, aperture photometry, and it's known also, looking at experiences with HST, to be underperforming compared to PSF photometry. And so this, on one hand, this is nice because it ensures that you get your appropriate signal to noise, but it is something you might want to take into account, for example, if you care about observing time, location efficiency, and design efficient programs. So yeah, I encourage you to talk to me, and there's all of this material is coming in current or upcoming papers from the collaboration.
All right, this concludes our program for today. Let's see, I want to thank everybody for your engagement, especially on Slack. I think that's working pretty well. Feel free to comment, make channels, whatever. That Slack instance is for us, so you can do what you want with it. Let's see, there's a list of some restaurants that was posted into the general channel. I encourage people who are looking for somebody to go out to dinner with or some place to go to come up here and mingle and form parties if you want. Tomorrow we'll do the same thing over again for people who are in person registered. There'll be breakfast from 8 onwards, basically. We'll begin the session at 9. Just one more day, so we're going to get through all the rest of the talks tomorrow. Yep. I want to, before I forget to do it again tomorrow, I said it once, but I'm going to say it again. There's 2 or 3 people sitting out there with computers right by the entrance to the cafe who are just spending their days hoping that when you come out for the break or the lunch, you will give them feedback. So if you have a moment, if you haven't yet, the search interface for MAST and the JDA Viz folks would like 5 or 10 minutes of your time.
We are still missing many talks for tomorrow, so please upload them.
Yes.
Send them via.
Yes.
Otherwise, it's going to be a short day. Or
No,
maybe that's what you want.
Don't tempt them. Don't tempt them. Yeah. I'd like to say the deadline for uploading your talk is before dinner tonight, but it's not. But it is before the session starts tomorrow. So I mean, if you could send it, if you have a morning talk, especially if you could send it tonight, then when the folks come in the morning, they can get the stuff on the computer. Did you have more, Marco? I will add to the list of restaurants, which are all pretty good restaurants, also 36th Street Avenue. I don't know what it is. Street, whatever. On the other side of the park. On the other side of the park has a ton of nice restaurants. So if you just get out Google Maps and look what's over there, that's a nice area as well. All right, thank you so much.